Welcome to this Quantum Security and Defense presentation. Thank you for being a valued member of our community. Alain Chancé is the president of MolKet SAS, founder and CEO Quantalain SASU and Alainquant LLC, business management consulting startups. Taha Salim is a lecturer and researcher quantum education officer at Amsterdam University of Applied Sciences. Joe Reddix. Joe Reddix has over 57 years experience in IT and emerging technology and is the CEO of Reddix Group.
Thank you. So I published I published a book, Quantum Chemistry and Computing for the Curious, together with Dr. Alain Chancé, and there are accompanying Jupyter notebooks which are available on GitHub. And I've also published a paper, Quantum Permutation Pad with Qiskit runtime. I would also add that a couple of weeks ago I attended the IBM Quantum Developer Conference in New York. And so I've been in the quantum computing arena since 2020. Taha, your move. Well, Taha, yes, introduce yourself. Well, yes.
So I'm Taha Salim. I'm currently the Director General of MolKet SAS together with Alain Chancé. And I'm also a lecturer and researcher at Amsterdam University of Applied Sciences in the specialization of quantum computing and quantum technologies. Recently also we got accreditation for a new master in the Netherlands and in Europe because I'm based in the Netherlands, in Amsterdam. And this new master is now accredited from 4 universities in the Netherlands for to deliver and also bring quantum workforce to the market by equipping students with knowledge about quantum computing and quantum technologies. And I was co-developing of this master in particular for the quantum software engineering track. Recently, I finished my PhD in quantum theoretical chemistry and quantum molecular dynamics, where I worked in projects related to James Webb Space Telescope. And I hold a master in quantum physics, lasers, and materials from France. I was also was co-speaker in several international talks, including JuliaCon with Alain in 2024. Also give presentations in APS March meeting and also like Washington DC quantum computing meetups. I'm part also from other networks and societies. Give some talks there like the Dutch Chemical Society and the Dutch Astronomical Network. And of course the Dutch Chemistry Conference and so on. So there is also several memberships and yeah, I'm also eager to present together with Alain and Joe today. Okay, we go.
So maybe, yeah.
Yeah, so now in MolKet, we aim to make chemistry simulations easier and faster using artificial intelligence, quantum computing, and high performance computing. MolKet SAS offers management consulting and AI services for quantum molecular dynamics, cryptography, and neuromorphic-based computing with cloud-based hybrid HPC and quantum computing platforms. This is also reflects our vision by bringing quantum designs related to chemistry and material design, leveraging the current state-of-art technologies. Yeah, so.
Joe.
Yeah.
Okay, hello everyone. I'm Joe Reddix. I'm the president and CEO of the Reddix Group. As you can see or read, I've been in this field of information technology since 1967. I actually got into it in the Navy as a data processing technician, stationed at the same place where Snowden stole all that information. So this idea of cybersecurity and information integrity became very important to me. I worked heavily with the Biden-Harris administration as far as this concept of master systems integration, which integrates a lot of the most innovative technologies we have, including AI and quantum, I'm a member of the Quantum Security Alliance, and the founder of the Quantum Security Alliance is the CISO, the Chief Information Security Officer of the Air Force. So we do a lot of work in that area, and I'm actually so close to Fort Meade and the NSA, I can walk to it. So my main focus is actually on, if you look at the use of the technologies, I honestly think that it is more strategic to look at digital warfare strategies and things like that. I actually have courses or teach for the high school at Fort Meade. I'm a member of the ACP-IAC Quantum Knowledge Group, which is a combination of the federal government and the private sector here in the DC area. Actually, it's more global. The high school at Fort Meade has just went through a $140 million renovation, and a lot of the capabilities of quantum, artificial intelligence, and bundled into autonomous technologies are some of our major focuses. I'm a member of the Small Business for America, which actually is a group that is located here in the U.S. and does a lot of the small business initiatives with the current administration. I'm an advisor with the Montgomery College, and on LinkedIn, as you can see, I've been in the top voice environment for executive management, information management, and management consultant. I've been in IT for 57 years and have never lost the passion for it. And with this integration at the molecular level, I'm looking at what we call a origin to memory strategy, which clearly at the molecular level will be used for quantum sensing and things like that. I honestly believe it would be the forefront of where we go from artificial general intelligence to artificial superintelligence, which is one of my main focuses. Thank you. I guess I can keep on going here. And this is just a summary of what we're doing. Partnerships is key. The Redix Group is actually a network that I started about 20 years ago, and I'm actually been on LinkedIn for over 20 years, so you can see a lot of the presentations and materials and things like that. And actually, I've helped design some of the aspects of LinkedIn over the years. Now, skipping down to our mission, and looking at the in-memory computing capability, we can talk about it later. This is very, very key to our overall strategy of origin to memory. And the idea of being able to have the more in-depth look at algorithm strategies, the logic boundaries and things like that at origin, in other words, where information is actually created, is extremely important to our overall strategy. And what we're looking at from the standpoint of moving again from artificial general intelligence to artificial superintelligence, basically mimicking the same way we as humans learn. And of course, you have your strategies with neural networks and things like that. We'll discuss that later, how it fits into our overall thing. I guess that's it for me. Thanks.
So
Tara, please go ahead.
Yeah. So now we come to MolKet's offering, and we started by introducing the idea that optical fibers are vulnerable to physical tampering. We all know that, and the solution can come from quantum chemical sensors that can detect wire tapping. So here is an idea of how this would work. With quantum sensing, we can detect the variations in optical signal induced by wiretapping by third parties. And this would serve as a probe for the quality of the optical links as well, and it can be used to create an encryption. If we look on the right, if you have an optical signal that enters an optical fiber, you can have you can have an untampered signal, and so if the optical fiber is clean, then you get a signal, and then that's untampered. But what if someone tampered it? It's very hard to detect this tampering sometimes with devices. So the only way is if we have some sort of a chemical sensor in between on the optical fiber that can detect the tiny variations in the optical signal. And that chemical sensor would give a hint in the form of emitted photons or some kind of small short electric pulses that would tell that something happened between these two end points. So how this quantum chemical sensors work? We put forward a conceptual idea for ultra cold gases as a good candidate for quantum chemical sensor. Now let us see. Quantum chemical sensor can be implemented or can be visualized as two-level system. So we can have a ground state and excited state. And to go from the ground state to excited state, we need this short quanta of energy, which is related to or represented by the famous formula energy equal Planck's constant times the frequency. And we can represent any quantum sensor via well-known Hamiltonian that includes a standard Hamiltonian for the system, Hamiltonian that represents the signal of the system associated with the signal, and also a control Hamiltonian, which is associated with a third party that does a control or does a probe on this quantum sensor. On the right here, we see a conceptual illustration for this quantum chemical sensor. So if we have an optical link represented like this, by having ultra cold gas in between the two endpoints, we can detune or make sure that this ultra cold gas doesn't interact or doesn't absorb the signal or the energy of the signal directly in the good shape. However, once someone tampers with it, the profile of the signal would change and will be altered, and there will be tiny variations that will be introduced in the envelope, and this ultra cold sensor would detect that, this as well, either by absorption of some energy or by emitting some energy, and hence that would sense the variation. And here we come to our idea. We were working on CO, or as a candidate for a quantum chemical sensor, because it's a simple molecule, but also it's also easy to control. And here is a simple Hamiltonian for CO. This is a simple Hamiltonian for a vibrational energy level. So we have a ground state of CO in the vibration, and we have excited state. And any energy that would be that will be off the ideal signal in the optical fiber could be absorbed here, resulting in excitation. And when the molecule gets excited or de-excited, then that will give an idea that there is some change happened in the signal profile. And this changes could be recorded and detected on external chip on board with the sensor, and would give a hint that something, some tampering has happened. It could happen naturally or artificially by wiretapping the link.
So now how are we going to design this? Well, the key idea is simulation. And we intend to achieve the simulation with physics-informed AI, artificial intelligence packages. So the working mechanism of the quantum chemical sensor, as explained by Taha, could be simulated using quantum molecular dynamics packages. A good example is Google DeepMind, Ferminet. So Ferminet is a neural network for learning highly accurate ground state wave functions of atoms and molecules using a variational Monte Carlo approach. And we have done some experiments with Ferminet. It also uses the famous transformer architecture, but the key difference with popular generative AI packages and large language models is that the input is physics data, chemical data. Okay, next one. And so the idea, which has been brilliantly explained by the CEO of NVIDIA, is a universal function approximator. So what we are trying to achieve, and there is a demo available on our website, and if we have the time during the Q&A, maybe Tara will present a walkthrough. We can deal with the computational complexity, which slows accurate and innovative simulations by replacing this computationally expensive part of the simulation with physics-inspired neural network. So on the right-hand side, you see that there are two inputs. So one input is typically the data that is needed to train a neural network. And then once the neural network is trained, then with data pertaining to the molecule or atom or system we want to simulate, then we produce the output. So it's the software 2.0 approach put forward by NVIDIA, but also this is something which IBM, for instance, put forward. And this would enable us to make simulations faster and that are also efficient and accurate. Okay, next one. So as I said, there is an example, I would say a proof of value of this approach, which is available on MolKet, which is available as a package. J stands for Julia, so it's a Julia package. It has been developed in Julia for performance reasons. So we have designed a quantum simulator to perform chemistry calculations with quantum computers or simulations of quantum computing running on classical hardware, and with machine learning. I would say it's not only or not limited to generative AI, but it leverages field-proven, I would say, classical AI approaches like neural networks. And what we have done, and it's still work in progress, we are building a generic scheme for computing molecular vibrational wave functions, providing the frequency and the potential. And here we have used off-the-shelf neural network surrogate package from Julia. And we were able to reproduce very accurately the calculations made classically. And this is this is available as a Jupyter notebook, and it can be accessed through the MolKet website. Thank you. So our vision of the system integration, we hold the view that the quantum chemical sensors could be integrated with optical links in an optical communication system. So that could help in detecting tampering with optical links, wiretapping the links, and altering the laser signals. It could also help potentially in encrypting the signal as well by providing RNG-like. So RNG stands for random number generator. So by providing RNG-like sequence generated from the excited states of molecules. So it's really a physics-based encryption, and this is a very exciting area. And next we will move on for Joe with his presentation of integration. Up to you, Joe.
Okay, thanks a lot. I can provide a better representation if anyone wants it from this particular panel. But the idea of this in-memory computing came to me years ago when I worked on the IBM 360, 370. Actually, I'm pre-JOS, so I go way back on this, but memory has always been extremely important, and the management of memory and information has been very key over these decades. Now, you can see up in the upper left-hand corner, a diagram that is basically what memory would look like from the standpoint of how it would map into different sectors of process and things like that, whether it's natural language processing, whatever. This is kind of like how we look at memory, and both memory from a quantum and a classical perspective. Initially, I looked at this as a way to augment some problems with the National Nuclear Security Administration and the way that they were managing data in memory, knowing that processing capability without placing the ability for memory and storage, to perform at an optimum level. So we came up with the strategy of saying, if we're going to look at blending between classical and quantum computing and providing a bridge, we needed a way to be able to share the information and to be able to map it into some tangible value. So if you look at this, you look at quantum computing as a way right now we feel will be heavily used for optimization. And that's extremely key. Now, the idea is you're going to have optimization at a quantum level, you're going to have a classical environment that can perform at a certain pace that will be applicable. So originally I looked at exascale, Frontier, now El Capitan, and actually with Lawrence Livermore taking possession of the exascale El Capitan supercomputer. It looks like this mapping is coming into place. Now, we will always need classical capabilities. So we're looking at interfacing with our molecular sensors and quantum systems and things like that, knowing that they're going to propagate like I don't know what, you're going to have an extremely fast, high performance environment. And that environment, of course, could be networked. Now, if you look at gathering the data from origin, sensors and things like that, autonomous technologies and all, and processing, and what we were talking about earlier with simulation, clearly that classical to quantum bridge is an excellent strategy for simulation. Now, the idea here is increased security and things like that. So anything you're bringing into both the classical and quantum environment, as far as this in-memory computing, will of course have a quantum cyber signature. And that's kind of like what we're developing with the federal government. And Air Force here in the States has been given charge by the Defense Department as the quantum lead. And like I said earlier, the co-founder of the Quantum Security Alliance is a CISO of the Air Force, and his architect, Dr. Merrick Watchhorn, is also, part of the Quantum Security Alliance and brings a wealth of knowledge, well over 30 plus years of capability to help us design this out. So what you see here is what we have presented to the Midwest Micro Electronics Consortium, which is funded under the CHIPS and Science Act. So trying to get that lead back and circuitry and things like that is extremely important. So we said, okay, we're going to do that. Let's look at it again from a twofold perspective, integrating it from the classical environment and the quantum environment. So this is kind of like one of the projects we put forward, and actually I think it's very conservative, but the idea is to get this started of integrating these technologies and not trying to replace one with the other, but optimizing the capabilities of both environments, being classical and quantum. And this is kind of like a 5-year plan that we put together, with the end results being an extremely robust, low-level latency strategy, high performance environment, integrated environment from source, which could come from autonomous technologies and things like that. Of course, we talked about sensors. I am a FAA Part 107 certified drone pilot. And the idea with that is that form factor ultimately will integrate both from what we want from an analog perspective and a quantum perspective. So if you look at placing those kinds of capabilities in something as mobile as a drone, you can see where this is going. Okay, next slide. Okay, now this is an older version, what I've been working with NVIDIA. I'm actually in the NVIDIA Inception program and the software development program with what, 3.5 trillion in market cap. I don't think they're going anywhere. So the idea was to say, look, if we're going to do this, let's look at the software development that's integrated into a use case, and actually use multiple use cases. This is integrating all of the defense services, Marines, Navy, and all that kind of stuff into using the predefined models and taking it into event training and things like that under this NVIDIA strategy. Now, NVIDIA is very robust with a number of different simulation capabilities and things like that, including a quantum simulator. But the idea of being able to take what exists already, be able to consolidate it into a pattern that could be used across all the different services, and of course, with leadership and things like that, like the Secretary of Defense and all that, and be able to do it in memory. Now, the reason why I use Gigaspaces is because Gigaspaces is one of the vendors, and it's out of New York, but it's heavy Israeli influence. But the idea here is that everything resides in memory. So you have your system record or things like that, your data and all that is in memory that you need. You have a digital integration hub, all that's in memory, and it's controlled in memory as a high-end memory management capability. So that sits on top of your microservices and things like that. It's extremely fast because, again, it's in memory, so you have very, very low latency. Now, I took the idea of using gigaspaces and say, if we have this kind of a mapping, say from a quantum computer standpoint, whether it's IonQ, whatever, the idea is to be able to have that performance in memory connected to, from a quantum perspective, connected to a classical version of it in memory. So I use the idea of gigaspaces because they're heavy in the financial industry, Chase, Morgan, and Morgan Stanley, and people like that. The idea is that those type of transactions are highly interactive. So he said to himself, okay, there's definitely latency oriented, and that's extremely important to this overall strategy of latency and performance and quality of input. So I've been working with both the industry SDKs and the NVIDIA AI toolkits and looking at how this could map together. And of course, here using DevSecOps to bring all the security aspects in. But this just gives you a high-level capability mapping of how we can tie all this stuff together. And of course, sensors and other input of information could be, applicable. And then autonomous data gathering is that I've developed some algorithms that are capable of learning from each other and integrating information from multiple sources. That's what you see here, the DoD environment. Digital warfare strategies is kind of like one of the things I looked at and being able to do this because of focusing on special operations, tier 1, tier 2, tier 3 operators, their need coming up for augmented reality, virtual reality, and mixed reality, things like that. But that has to be high performance and as near real time as possible. So it's kind of like this scenario here is designed to work in kind of like a near real time fashion and sharing information. So your decision makers over here on the right, whether it's medical, whether it's autonomous vehicles, whether it's visual, things like that, it's extremely fast and extremely robust and extremely shareable. And like I said, the algorithms here are the more in-depth lines of code that you would need to make all this happen. And I go back to that origin to memory strategy. Origin to memory is not just at the edge level, it's all the way through the pipeline of where information flows. So you have that origin to memory mapping to increase high performance, throughout the food chain. Now, I clearly believe the major issue we're going to have is capacity of data centers as it relates to energy. So one of the things I looked at is that we're going to have to tie energy and energy simulation and things like that at the molecular level, at a circuit level and things like that, be able to offset some of that power requirements of the data centers, because if you can't turn on the light in your bathroom, you can be in trouble. And I know AI is important when you're sucking up that much energy. And as you can see, AI is really creating an issue dealing with data centers and the power consumption itself. So part of this is looking at how can we manage all of that stuff, especially energy. So one of the circuit level designs we have is the energy processing unit. And the energy processing unit uses things that you would have with quantum level simulation at the edge and device level to be able to look at energy, look at things related to detecting security breaches, as we talked about earlier, dealing with fiber optic. But a lot of that is taking some of that energy consumption deeper into the origin, be able to offload it, through the pipeline, therefore reducing the power requirement, for example, at the data center level. Okay, next slide. Now, this is my master plan. Okay, I know it looks like it's kind of large, it is, but it has to happen. So integrating the forces and things like that, the knowledge sharing across all of the defense posture is extremely important. The DoD, looked at it from the standpoint of multiple layers, the API at the top, talking to your clients and your stakeholders and all, the operating systems, the networking and things like that. This has taken me years to figure out how to do because it's not necessarily as seamless as it should be, but it's headed that way now with artificial intelligence and training the warfighters and simulating information from the different services, best use cases, using AI and things like that. Now, I'll tell you why this is important. If you look at where master systems integration, which is a key to the Reddit group overall concept, you have artificial intelligence at multiple levels. Let's think if we look at the hearts of those AI strategies and we group those AI strategies into, say, a high performance prime. I call prime as kind of like my strategy for a high-end network capability. The ability to use the heart of the AI, say from a Google, say from an AWS or whatever, and build a composite environment so that that data is shared at an extremely detailed level and be able to again, do the simulations and things like that, which I think is going to be required for training things like quantum and all. So simulations is extremely important in this whole scenario, but shared simulations. So whether it's NSA that has a heavy emphasis in using AWS and Microsoft and all that kind of stuff, the idea of being able to share that on an AI level is kind of like the way we looked at bringing all this together. And then, of course, you have your sensor data and all, which I think is going to grow even more over the years. So by the year 2030, 2035, for example, groups like PricewaterhouseCoopers is saying that the gross value added of AI alone is somewhere north of $15.7 trillion. Now, there's a lot of emphasis in making sure this stuff is right, because whoever gets this kind of scenario right, for example, at the defense level, is, put it mildly, like Putin says, is going to rule the world. And, as well as I do, we got to do this the right way because AI does have the ability to create hallucinations and things like that. And across this environment, that could be extremely deadly. Okay, next slide.
So for the audience, we've put together in this bibliography a selection of papers more focused on the security, the vulnerability of fiber optic transmissions, fiber tapping, and data security. So and there is also about cable wars. The agencies involved in tapping submarine those cables that run under the sea. But if you read these very interesting articles, you will find out that the most vulnerable points are not actually buried deep under the sea, but rather on Earth before the signal goes through and underneath the oceans. Now, what's interesting is there is a lot of documentation about how to hack fiber optics, but there are not so many interestingly, documents, articles, or at least that's our results of our searches pertaining to countermeasures, and especially countermeasures leveraging quantum technologies. There is a paper, the last in the list, about secure optical communication using a quantum alarm. But that's interesting, and I guess this could be a good topic for discussion. So our offering and the integration, brilliantly put forward by Joe, is presumably cutting edge. There are not so many articles. It is worth mentioning, and we had the discussion with Taha about this, is that there are some constraints, limitations, which what we can achieve with quantum molecular sensing. However, our discussion around simulations of physics system would apply equally well to other quantum sensors, for example, nitrogen NV center quantum sensors, for example. So this is a short bibliography for those who are curious about how what is the risk and how can someone tap into fiber optic cables. I would say it's not just of interest, of course, the defense industry, but it's potentially of interest to any company who cares about the confidentiality of their communications. You just need to have a look the way the fiber optic cables get through your home or your company, and you will understand that it's really vulnerable, at least in some countries. That's it. I guess now we can move on to the questions and answer. Oh yes, there is an appendix, maybe. So maybe Joe, maybe a short comment about this extra slide in appendix.
Yeah, yes. This is the vision. I know it's down the road a little bit, but we need to start now. This is what I see will allow us to get to artificial superintelligence using the universal quantum environment. Now, to be honest with you, there's going to be multiple quantum scenarios where it may clearly not be one vendor. When we look at where we want to get as far as secure computing, that's at the top. If it's not secure, we're not going to be able to get this off the ground. Machine learning is capable because of the high performance environment. So we see that speeding up. Quantum chemistry, and we're down at a molecular level right now, that's really going to grow because these sensors are going to be extremely important to develop the quality of information that is sent through the pipeline up to the decision maker. Then optimization problems. And I like optimization because you can use it from designing shoes to airplanes to speech patterns, all these kind of things that you look at. The optimization capability, I think, will be the first way we see these high-end quantum systems, activated into a real set of use cases, in other words, things can really work. And then if you look at the ability to train, our workforce, and what I'm saying with this, because with a robust workforce that understands not just the mechanics of the technology, but the economics of it, because there's trillions of dollars in what we've been talking about. And the idea of who's going to get there first and why and how they're going to use it, it's got to be on people's mind because it can be used for both, I want to say this, AI and quantum can create and it could destroy, it could do both simultaneously. So it's up to us as practitioners and subject matter experts to take that to the more positive side of it. Now, the ability to build this environment, this is where we need a collective capabilities and people, for example, that are on this call. This is reality. This is going to happen. It's going to happen a lot faster than people were thinking because, like, I've been using AI to design and concepts for the artificial superintelligence with Copilot. And it really works because when you look at what it's saying, it's going out there taking all these different ideas and mapping them together and things like that. So it's helping you create what's going to be the follow-on to it. It's kind of like a vision of it. Okay, that's it for me on this one.
So that's it. Now is the time for questions and answer, and I leave it to Taha and Joe to lead this session, questions and answers. Thank you. So don't be shy. I think there must be lots of questions, curiosity.
So I see the first, there is two, okay, couple of, I think, questions. The first one, how is the noise on the line distinguished from someone tapping the message? So that's also a great question. So maybe I can start the ball rolling for this one. In our case, we know in what would be the typical noise profile for the signal, and this we would know. So we have to model the signal first, and the typical communications and the network lines. And once we know the signal profile, when this changes with some probabilities, is like so there is also some part of machine learning is incorporated. We would know that there is some variations that high likely is not a result of the noise, and it is because of someone is trying or is already tapping the wire. So the profile of the signal would change in a sense that it will give a profile that would not result normally from a typical noise that's associated. The second thing, it also could be a good indication for the lifetime of the optical fiber, because once the typical noise profile is not there anymore and there is a new profile of the signal is detected, that can give an idea that, for example, some earthquake is happening or this optical line will die because of something happened, might be also naturally to the optical fiber. So in all cases, we will know the reference signal, the reference or the typical noise profile, and the change that would happen to these typical lines. Hopefully this answers the question of Reg. Yeah, thanks, Reg. Thanks, Greg, on the question. There is also another question from Amara Grabs, if I pronounce the last name correctly. The question says, is there not a visibility study about the countermeasures to fiber wiretapping? As a citizen of a country, LV, which is watching 2 DK and 1 DE and 1 SCE defense ships, that stopped a Chinese ship that's suspected to have cut two telecommunication lines in the Baltic Sea. So, yeah, okay. So there is, as far as I know, there is some visibility studies that have been done for countermeasures, but of course, depending on the efficiency. But maybe Joe, if you have some recent information about that.
You answered it pretty well, but I think if I say this, one of the problems that we run up against as far as is use of the technologies, again, it's very important to understand the integration requirements. And the reason why I'm going to that is because there's so many vendors going after these solutions in different fashions that if we look at combining a lot of the research and the knowledge together, and this is one of the problems we've had here in this country, that everybody's going and looking at the monitoring piece of it, but being able to optimize a solution that could be shared and shared globally seems to be lacking. Now, what I'm trying to look at, because how can I say this? The reason why these problems are so pronounced, I guess, is because we are looking at strategies to benefit maybe our own efforts and things like that, but not a collective. So what I'm trying to do with this is to look at how we can look at all these best practices. And I've researched this a lot online. There are enormous amount of papers, but they come at the same thing in different ways, but they have some good points. But being able to take these kinds of forums and take them into a reality that is extremely shareable and honestly use as a developing tool for the workforce to solve some of the things that you're bringing up. This is what I'm finding the hardest thing to do, okay? The problems we're going to have going forward is that some of these technologies or solutions are going to compete with each other, and the quality of the end product may be diminished if we don't watch it. So leadership is kind of like the main focus, I guess I'm trying to go with this conversation, and looking at it from the standpoint that it's not too late. And it's definitely not too late to bring up our workforce so they understand that the goal, and I can say this, is a highly diverse approach. Over the decades I've been at this, the ideas and the solutions that I've seen coming from different people have been like a fabric or different ways of building a fabric. And the only issue has been in being able to combine it is funding and things like that. So in summary, we have an opportunity here that is immense. We got to really realize what's happening when we're looking at the emerging technologies as a whole. We are on the cusp of being able to create not just weapons and things like that, but I'm right down the street from Johns Hopkins. I'm right down the road from the ability that created the some of the COVID vaccines and stuff like that, so the biomedical industry. What I'm finding out is a lot of this knowledge and capabilities are so important to humanity as a whole, okay, to get right. And like I said, I've been at this for 57 years, and I'm watching the ability to both create and destroy. And I'm saying to myself that if we're going to move ahead as humanity, this is kind of like the forums. We're going to have more and more and more of, okay? When I first started in this scenario, it was not evident that people that look like me were going to be capable of being in it. But I'm going to tell you something that I never said to too many people. Years ago, when I first got into this, somebody told me that people that look like me wouldn't do well in this field. I'm at it for 57 years now. They have designed systems for American Express, United Airlines, Wang Laboratories, General Dynamics, BA, all that stuff. So you did all that work, but it's lost in other things that you can't put a technology around. It's humanistic. It's kind of like, if we come up with all these great ideas, where's the issue lost? But why can't we share? Why can't we bring these kind of solutions? So I'm looking at something here about hemoglobin, and I know I've had some issues with my blood. I'm 75 years old. But I think that a lot of the stuff that we're doing is really important for us to look at a seamless work ethic where we can share this stuff, okay? There's a question dealing with fiber and the wiretapping. Let me say this. It's not defibrillator and all that stuff. I mean, people have different reasons why they're coming after the value of information. And in looking at how we can protect it, it's kind of like the overall umbrella. Cybersecurity at molecular level is so doggone important. It's hard to say that origin and source protection has to be as robust as you breathe in the next breath, that kind of thing. So what I'm looking at right now, to close it out, is that I really want to work with things like what I see here and be able to solve these somewhat complex problems for the next generation, if we want to have a next generation, okay? I know I got off topic a little bit, but that's extremely important to me, because after all these 57 years, it seemed to be the most major problem, okay? That we weaponize the wrong thing for the wrong reason, and all of a sudden we get in trouble and then we can't back out of it. I see it happening here in the US and stuff like that, where we're moving into directions that are so diverse and different from what we originally started with as a country, for example. And I think we see some major problems get ready to happen. So being able to pack this stuff that we have here in the chat, it ain't going to happen unless we have an ability to be able to deal with these up and coming issues, if you know what I mean, okay? And I'm sorry to get off, but that was important to me, because we can't go nowhere without being able to bring it together, okay?
Yes, thanks very much. Yeah, thanks very much, Joe, for this nice and elaborative answer. So thanks, Greg and Amar, for the questions. We have a question also from William Slater. Hopefully, I also pronounce the name correctly, because also there is other pronunciation for Slater determinant, so it's also Slater. So the question says, wouldn't the CO2 molecule or the NO be safer than CO? And William states a few reasons why, for example, CO is not good, especially from a health perspective and a benchmark perspective. So the short answer about CO is just a benchmark molecule. Of course, a CO2 could be better. The idea is that it's more complicated. So the PhD I finished was on CO2. So the theoretical and the computational work involved with the CO2 was really significant, especially with the several molecular vibration. It has 4 vibrational modes. 2 of them are degenerate, so it can bend in plane and out of plane, and there is vibrational angular momentum in it. So it could be a good candidate, but of course it would require more time to develop a software. So if there is a collaborator or a customer who's also interested in exploration of CO2, this is something we can definitely go. But for the CO, it was just to have a small molecule that's easy to emulate, especially with AI, because we wanted to make like a universal function approximator, as the CEO of NVIDIA and Alain also said about it, which is you give a frequency of a molecule, and then the small routine of the machine learning would predict for you the energy eigenvalues and the wave function, which can be used further in the simulations. So instead of spending a lot of time on the theory part, it can give or spit quick information about the molecular properties that we need. So that was also a good molecule for benchmark. The second thing about CO, we use it in limited quantity. So if it is in this conceptual use case, it will be, for example, in very small chamber, like a small cube or something that's connected to external chip. And as Anna pointed out from our discussion, that also could be used in universal cybersecurity, like in VPN vendor, external VPN vendor. It could be used also in homes, integrated with the modems, the internet, the devices that receive the optical fiber and convert it to the Wi-Fi signal. So it can be there at the entrance where it can tell information if there's something happened or not. So there is many ways, and the idea is that we have a very small device that could be encapsulated in the router in the home. So hopefully this answers the question. So there is also another question from Abdul Ali Tal. And the question is, what are the technical challenges quantum simulation problems are facing, and how does MolKet aim to tackle them? So thanks, Abdul Ali, for the question. As also Joe explained quite clearly in his presentation about there is also need for development. And part of that is how to reduce the computational complexity, because we know physical laws by heart. We can apply them quite rightly to small systems. However, when we go to industry, it's the problem is about the scalability and how we can apply them to more complicated systems and much bigger systems where they are relevant to the industry. And hence, simulations or accurate simulations would require a significant time and computational resources. This is why most of the time developers go for approximations, which sometimes work, sometimes not, depending on the use case at hand. And to tackle this computational complexity, we also not also to trying the work on theory. We do it for sure, but also to do some work on the computational side where we can integrate AI and ML, as also Joe explained in his diagram, in the simulation, where we see which part is significantly expensive from computational perspective, and replace that with a well-trained physics-inspired neural network which can like replace that part. For example, in the CO example that we have been discussing, to generate the wave function and the eigen values to the spectra of CO, we need to do what's called variational calculations. And these for bigger or larger molecules, it's very time demanding and computationally expensive. However, if we can train an efficient neural network on this part, that part of the calculation is gone, and then it could be done in less than a second by training very well physics-inspired neural network that is designed for this case. So this is how we do. Perhaps Joe wanted to comment on this.
One of the things I looked at with LPPCAN being an exascale supercomputer, enhancing the simulations, of course, at a classical level, but the idea is that the LPPCAN environment, the exascale, can help design the functionality and the coding for the optimum use of quantum. In other words, they can work with each other and build the bridge between the two environments. So simulation is not just one, it's for both environments. Actually, simulation, like we were discussing, could work all the way from origin throughout the whole process. Now, the key problems you can have with it is input is important, accuracy of the data and things like that, and reducing hallucinations on the AI and all that kind of stuff. That requires a heavy human effort, okay? I have not met an AI environment that can think like that. And even looking at the nuclear stockpile, for example, that the current supercomputers are doing, mistakes. But the idea is being able to simulate at various levels. So you may simulate what happens at origin, what happens at gateway from origin, what happens through the pipeline when you're transmitting. All that stuff can be simulated. And actually, it can be simulated individually or simultaneously together. But the thing I like about simulation is it is an enormous what if, because you know as well as I do, it can happen, it can happen. So you need that idea of being able to put things in there that may not be a practical problem now, but the AI and the environment simulates that problem as if it existed today. So looking at using the exascale and the classical quantum, we look at the simultaneous use of the memory. So that's what I'm trying to come up with, is a memory platform, whether it's material-based or whatever, that can be shared between those two environments. And actually, it could be miniaturized down so that same concept is something that we can use at origin. I know it sounds a little futuristic, but the idea of being able to enhance the accuracy all the way from the origin of information so that that simulation is as accurate as possible throughout that food chain is extremely important from my side, to reduce the kinds of errors that a simulation that goes wrong could cause, because a lot of this data has to be tested over and over and over. And the best way to test it is the human factor, as far as I can see, because I have not met an AI or an environment that can combine all that intellect that we have, for example, here. So I'm just saying, simulation is, we talk about it, we write it down, we put it into algorithms and things like into systems, but still the key is AI is not going to replace us. AI is because of us, okay?
So thanks, Joe, for the nice answer. So I would like also to mention that we, as Joe explained, we also work on like enhancing the administration with the memory and so on. So as Joe highlighted, so it's also requires how we organize the data of the molecular data that we are dealing with, and the equations and the ways that we even sort the matrices. And you can find it surprisingly that in some kind of good administration, we might save half of the computational complexity, for example, based on the way that's code and the algorithm is administered. Yeah, that's something indeed. And there is comment from Amara Grabs, and I think it complement Joe. She says 100% agreed. The OSINT community tracked exactly the Russian and the Chinese ships that are spying nearby, and OSINT community knew who cut the line long before anyone else. We are 100 people watching and studying that can be harnessed. Sharing solution is the best path forward. So please feel free, Joe, if you would like to comment on it.
I have to look up that word. That's an interesting one. I'm an old guy, so I looked at that. I said, okay, yes, to answer your question, I say this. This is where I think we as a group and developing our simulation strategies would be very important, because I can't answer this because there's so many ways that this can happen. And this is where the human would say, look, we need other humans and we need to input this into our systems to be able to figure out. I mean, that's the best way to do it. So yes, we do have the problems, but to solve those not problems, I honestly believe these forums like this probably are the best first phase. We're going to have them throughout this integration of technologies and emerging technologies, and we're developing emerging technologies. So yeah, I think it's going to be an ongoing problem, and it's one that combined with the tool or the resource of the emerging technology will be able to solve it. It's not going to go away. As we're creating these new environments, it's just simply going to enhance. Now, how do you solve it? This is my perspective. This is the K-12 beginning, okay? That's what we're doing at Fort Meade. Where we have a program where we're teaching not to be physicists or anything like that. We're teaching the integration of the knowledge of those people, including people like me that have seen the different environments put together. But to lower this requirement on the problems of errors and things like that and retro casualty, I think, like I said, if we start with the younger generation right now and bring these tool sets to their level, not necessarily, extremely detailed level, but bring this on so that that mindset is being generated, over the years to solve these kind of problems, and train the new researchers and the scientists and the people like me who are master systems integration persons that can, I believe, can help alleviate a lot of what we're looking at here as far as the retro parameters. Okay. But training right now is important because we lack it. We don't have enough resources to come up with what I just talked about here in our own country. I mean, it's really a problem, but it's not something that we haven't already discussed, or we're doing it right now. But to answer your question, if I was a teacher, we know we got to have the basic reading, writing, mathematics, and stuff like that. But these concepts of what the future is going to hold for the next generation have to be taught now. Okay. I don't know all the answers because I come from a background that was vacuum tubes, was 80 card columns and things like that. And I saw it grow to this. That's why I'm saying that a lot of these problems we're having right now are perfect use cases for why we need to put funding and training into the young ones, okay? To get their minds looking at this stuff and looking at things of using this technology. Hopefully that answers it, okay?
So thanks very much, Joe, for the answer, and thanks, William Slater, for the question.